next thing that we have, so we saw the principal quantum number, which is the size, the azimuthal quantum number, which is the shape. The next one is the magnetic quantum number. Now, this will give you the orientation of the orbitals. Okay. Now, what do I mean by orientation? Now, let's see. So, if you have a spherical shape, okay, so there is only one way in which you can place that. Okay, so there is only one possible orientation. So, for an s orbital, this is represented by m. So, for a spherical orbital which has L, the azimuthal quantum number of 0, how many number of m's are possible? The number of m's. Only one, sorry, only one. How many types of orientations are possible? There's only one orientation possible. And what is that m? So, this goes from minus L to plus L. In this case, what is the L? 0. So, this will only be only one number, 0. So, it has one orientation, and I represent the orientation with the digit 0. That doesn't mean it has 0 orientation. It has one orientation, and I represent that orientation with the number 0. Okay. Now, let's move to P. Now, if this is P, now you see that you can represent this in many different ways. Now, let's try that. So, let's assume you have an xy axis like this. So, you have x and you have y. So, you can have the orbital like this. So, you can call it a px orbital. You can orient the orbital in this direction. This becomes a py. Okay? Now, there is another direction which is the pz, right? So, this is, I have not represented the z in these, but they do exist, right? They do exist. Okay? In here, you can have it along the z direction, right? So, this becomes a pz. Okay, so how many orientations were possible? There were 3 orientations were possible, right? So, the number of orientations were 3, and which will go from minus L to plus L. So, what was the L of P? The L of P is 1. So, this will go from minus 1 to plus 1. Okay? So, there are 3 orientations possible, and what are those 3 orientations? A minus 1 orientation, which is the px, a 0 orientation, the py, and the plus 1 orientation, the pz. Now, it's just a name. It is not necessarily that px is minus 1, and it cannot be 0 or 1. It can be anything. It's just a way of representing minus 1, 0, and 1. Okay. Now you have a d orbital. Now, okay, just moving back, you saw that for the s there was only one orientation possible. And I tell you that one orientation is the reason you had only one room in S-type suite. You had 3 rooms in P-type suite, right? And these 3 rooms were basically the Px, Py, and Pz, right? And this is basically minus 1, 0, and plus 1. So, any electron that is coming in here will have a magnetic quantum number of 1. It will have the azimuthal quantum number of 1. In here, the magnetic quantum number is 0, but the azimuthal quantum number is still 1. Why? Because it's still the p orbital. It doesn't matter which room, it's still the p suite. So, the suite number is still the azimuthal quantum number, which is 1, but the room number, or which is the orientation, has changed. Okay? Now, without even blinking an eye, now we can say what will happen for the D. Now we saw that D had 5 rooms. The D suite had 5 rooms. The D orbital has 5 orientations, right? So the azimuthal quantum number is 2. So the quantum numbers will move from will range from -2 to +2. So it will range from -2 to +2, right? So this is D. Now let's see what are the different shapes. Okay. Okay, so if you have something like this is X and this is Y. This is dxy. Okay, you can have one orientation like this. Okay, now similarly, if this is y and this is z, and if you have something like this, this will become zy, right? So there will be a third one for xz, right? So this is dxz. Okay, we have 3. Now we know that there are 2 more. What are those? Okay. The 2 more are xy. Now you can have something like this. This becomes dx square minus. These are just names, okay? We'll understand in detail what this exactly mean and how we came up with this. But for now, let's just remember, okay, these are just names of how things are being arranged, okay? And we are only one remains. This is z. This is one of the weirder ones in which it has a donut shaped in between. And a dumbbell. So this is dz square. So you have 5 of them. Now we know that F has 7 rooms in the F suite, right? So how many orientations are possible? 7, and that is why you have 7 rooms, right? 7 different orientations for the 7 rooms. And from what will be the range? It will range from -3 to +3. So it will be -3, -2, -1, 0, 1, 2, 3. So 7 orientations for the 7. So this is basically the magnetic quantum number. Okay, this is just giving you the orientation. So the principal quantum number gave you the size. The azimuthal quantum number gave you the shape. The magnetic quantum number is giving you the orientations, and there is one more that is left, which is called the spin quantum number. This gives you the spin of the electron. Now we saw earlier that in one particular room, electron can go either this way, spin up, or they can go down, spin down. Now these are the 2 representations of the spin. So we will try and understand what this exactly means in the physics point of view when we actually see the electron spinning in one or the other direction. So the spinning, there are 2 ways of spinning the electron. It can spin clockwise, it can spin anti-clockwise, and that is being represented by 2 different numbers, +½ and -½ These are just the 2 different numbers in which which we can represent, +½ and -½ That's it. That's how we are going to represent the spin quantum number. Okay, so for any electron, we'll see an example soon in the next video, how you can give any electron a particular, any electron in an atom can have 4 quantum numbers associated with it. It will have a principal quantum number, an azimuthal quantum number, a magnetic quantum number, and a spin quantum number. Now, every electron will have these 4. Now, when you compare these four quantum numbers for all the electrons, you will find out that no 2 electrons will have the same number of no 2 electrons will have all the 4 quantum numbers same. It cannot. It won't, right? So 2 electrons can have similar quantum numbers. It can have either 1 similar number or 0 similar number or 2 similar or 3, but no 2 electrons will have all 4 quantum numbers the same. It will not happen. So those 2 will be exclusive, right? So the set of 4 electrons of quantum numbers for any electron is exclusive, and this is explained by the Pauli's exclusion principle. Okay, so in the next video we'll be trying to see how we can find. We'll see an example of how we find out the different quantum numbers, and what is the implication of the Pauli's exclusion principle, and we'll try and see what that means. Okay, awesome.